Welcome, everybody, to our July installment of the AIAA Space Resources webinar series. This webinar series is hosted by the Space Resource Technical Committee's Education and Outreach Subcommittee. I'm Jared Longfox. My co-host is and co-organizer of this is Joe Kenrick from Lunar Outpost. I'm at the University of Central Florida. Um, Today we have a really cool talk. Dr. Patrick Flowers is going to be introducing some of the work that he and the rest of the team at Redwire have been doing on one of their in situ resource utilization projects. I'll let him give more details on that, but as usual, everybody, please feel free to punch in the Q&A as we go. Towards the end of this, we will be actually doing a Q&A session. So if you have any questions that you have, you punch them in the Q&A. We will get to them in the order that they were received at the end of Patrick's talk. Let's see what else. If there are any tech issues, I don't think attendees can actually access the chat per AIAA rules, but feel free to punch it in the Q&A and I'll be monitoring that throughout. So with that, this isn't my show, so I'll turn it over to Dr. Patrick Flowers, the Materials and Mechanical Engineering Manager at Redwire Space. Thanks for your time, Patrick. I look forward to your talk.
Thank you very much. Yeah, so I'm Patrick Flowers. I'm based out of our Jacksonville location here, and I'm the principal investigator for the Mason project, which is what we're going to be talking about here today. Mason is a tool suite for lunar and Martian construction, and let's jump right into it. So I'm going to start with a little bit of a company overview for those of you that might not be as familiar with Redwire and what we do. We do a lot. So after a couple of slides on that, we'll jump right into introducing Mason. For anyone who isn't aware of exactly what we've been doing over the last year and a half or 2 years, and so give you guys a update on what Mason is and what we're trying to accomplish here. Then we're going to shift into a very important question and discuss why do we actually need landing pads? What's the need for landing pads needs to be really apparent and clear if we're going to be investing this much effort into the development of tools for making landing pads. Then we'll go into some updates on Mason development of the tools that the tool suite that we have and some of the testing results that we've had. It's going to be just a very brief, kind of high-level updates due to time constraints here. But we'll give you a sneak peek there of what's been going on, and finish out with some future outlooks and Q&A. So. Jumping into Redwire and a company overview here, we have Redwire is now a company over 1,200 employees after our recent acquisition with Edge Autonomy, and we have 18 facilities across the United States and Europe. I'll show a picture on the next slide of where those facilities are. We've got decades of heritage, and we've got our fingers in a lot of different areas. We touch pretty much every aspect of space. Everything you can do in space, we're involved in it in one way or another. So we've done lots of microgravity research. We were the company that did the first 3D printer on the space station. We've got over 200 parts that have been 3D printed. Over 250 missions have been flown, by Redwire. So, very, very proud of all the great work that Redwire does in space. And this is a snapshot of the different locations that we have. Again, I'm in the Jacksonville location here. But we are international. We have offices in Belgium, Luxembourg, Poland, as well as many offices across the U.S. as well. This is a another cool graphic that gives you an idea of how we how broad the impact is of Redwire and what we are able to support, all the way from areas like digital engineering and some of the very innovative satellites in the very low Earth orbit space, um, to microgravity research and LEO, and all the way up to communications and remote sensing, situational awareness satellites and MEO and GEO, and on into the moon and beyond, that we're involved in. So we're going to focus the this talk today on the lunar infrastructure development that we've been focusing on to help facilitate that long-term presence of humans returning to the moon and eventually to Mars. So let's talk about Mason. Um, Mason is a STMD project that has a tipping point that was awarded in the middle of 2023. And the objective for the project is to advance these state-of-the-art construction tools from Tier 4 to 6. And we're demonstrating the compaction, grading, and microwave sintering processes for lunar regolith in a relevant environment. We're trying to take, the fine, abrasive, harsh lunar regolith powder, and we're trying to turn it into this, which is a rock-like material that is strong and suitable for construction of landing pads, heavy infrastructure foundation, and more. We'll show a little bit of the applications on the next slide. But these tools are an important part of the way that we've been developing them is to make them as platform agnostic as possible. And the reason we're doing that is strategic, because right now we do not know all of these development activities are happening in parallel. People are developing rovers, people are developing robotics, different sorts of capabilities that are going to come together in the near future. But at this point in time, and especially a couple of years ago when we began the project, there's a lot of uncertainty as far as which one of those our efforts are going to be successful and are going to make it to the moon. So we did not want to paint ourselves into a corner and marry ourselves to a platform that didn't actually end up making it to the moon. So because all these efforts are going on in parallel, we think it's wise to keep our options open and to be as platform agnostic as possible. This also allows us to support multiple customers in the future if there are multiple platforms that we can add our tools to. So the major elements of Mason are, as I said before, we're doing grading, compacting, and sintering. The first tool is that grader tool. It's we call it Blade for Autonomously Surfacing Environments, or BASE, and it performs. It's the first step in the process. Whenever you go to a site that is raw, it's full of lots of craters and hills, rocks, then you want to take that and your first step is to just try to level out that site and to remove any rocks that you don't want present, fill in any craters, and get it ready for subsequent operations. So we will use the base tool to do that first, a very important operation. And secondly, we will come back with the compaction tool. Now, this is our planetary autonomous compaction tool. It provides our PACT. It provides scooping and compaction functions. Also has some filtering capabilities that can be utilized in that tool. Lastly, after we have uh, used the grader tool to level out and flatten out the environment and the compaction tool to really densify that regolith powder, we come back and we heat the material up to sintering temperatures with our microwave emitter tool. And we call that the microwave melter of Martian and lunar terrain, or MELT. So when we put all three of those tools together, we can accomplish a lot of very important things that facilitate long-term habitation on the moon and Mars. That includes being able to make landing pads, of course, uh, and it also allows you to make roads that will keep high traffic areas easy to traverse, and it'll be able to keep areas cleaner that you want to try to keep dust free. Berms will aid in that as well to try to shield the areas that shield from ejecta to keep a nice barrier between dusty areas and clean areas, as well as heavy infrastructure foundations. Whenever we talk about like vertical solar array towers or some of the larger infrastructure that's going to be necessary for some of these lunar bases, base of operations. They're going to need to have a very stable infrastructure foundation to be able to survive things like moonquakes and to have low risk that there's going to be any damage to these very important bits of your infrastructure. Right, so let's talk about landing pads specifically and why do we actually need landing pads? That's a natural question, and it's one that I get a lot because people initially think we've gone to the moon a lot of times already, and have not had a landing pad, and so we've actually been on 6 manned missions previously that were successfully landed and returned astronauts to Earth on these missions, and they didn't have a landing pad. So why do we need a landing pad? Well, it's interesting to look back at our success rate as a first point to address that. To date, we've had 59 attempts to land a spacecraft on the moon, and only 27 of those have claimed at least partial mission success. All the rest of them failed fantastically. So that's not a very good success rate. That's less than 50% overall success rate. So it's not easy, and the risk of failure and the amount of damage that you need to plan for in your cost estimates, your budgeting, all that sort of thing, your risk tolerance is apparently very high. And also to date, similar kind of story is in Mars as well. We've been made 17 attempts to land spacecraft on Mars, and only 8 of those have at least partial success. All of the rest of them failed fantastically. Whenever, as a first step to just answer the question of do we really need landing pads? We've landed on the moon before. It's helpful to point out that most of the time when we've tried to land on the moon, we have failed. And let's take a look at a couple of things that damage that occurs due to plume surface interaction, ejecta, that could be or poor visibility that could be mitigated and helped by having a landing pad. We'll look at those really quick here, just a few examples. So first of all, one of these manned missions, the Apollo 15 lunar module, actually had severe damage as a result of very poor visibility. They were unable to see that they were landing on the edge of a large crater and ended up with one leg of the lander hanging off the side. That tilted the lander at a pretty steep angle, and the bell actually came in contact with the ground, and you can see the crumple on the engine bell in the top right picture here. Let's see if I have a laser pointer. In this area, there's a crumple section at that severe damage. Now, In this particular mission, they didn't need to use this engine again for their liftoff. This gets left on the moon, so it didn't matter to call their mission success and to be able to return the astronauts back. But if they had to operate that engine again, they would have been in serious trouble. Um, so the next one is IM-2 lander's leg broke during its landing, and you can see we got back this one snapshot from the images where there's very poor visibility and lots of rocks and debris flying everywhere, and you can clearly see the leg that it had broken off while it's on its way down, trying to get to its landing. And then due to that broken leg, it caused it to tip over. Um, Now, the next one that I wanted to point out, this is actually one that's kind of funny. The Slim Lander. This is a one based out of JAXA. That it's actually on the bottom right here on its head. So it landed upside down, and it's meant to land on its side. This particular lander to have a wider base. But it had a combination of engine failure and steep grade of the terrain and rough terrain. So some of these issues led it to actually tip over whenever it was trying to land, and it ended up resting in this upside down position. Luckily, it was able to actually get the rover payload that it had out, and so this is an image that the rover took of the spacecraft after it exited the vehicle. So interesting to see it sitting on its head there on the surface of the moon. Next example I wanted to show here is some rover damage, and if you look at these sky cranes that were devised in some of our Martian rovers, this was meant to uh, give a very gentle landing to the rover and try to keep all the thrusters far away from the surface to minimize the impact of all that PSI. But as you can see from the picture on the left, it's still quite violent, and it's kicking up a lot of debris and dust, and the visibility is essentially zero as they're lowering this rover toward the surface. They can't see anything as far as where the surface is. And you even see in the final frames of the video where the rover is completely obscured. They have no idea where it is, and you see huge rocks being flung past the rover and up towards the sky crane, the spacecraft. The image on the right actually shows a debris scattered all over the deck of the rover after it has landed, and this particular rover, the Curiosity rover, it had one of its sensors, I think it was aft wind sensor, that was damaged during the landing, likely due to all this PSI and impacting some of the cabling, and was non-functional after the landing. So there's even whenever you take steps to try to mitigate and have minimal impacts to PSI by keeping thrusters far above and lowering things, that sort of stuff, you still end up with issues of it being worse than you thought and it having lots of problems with damage to your hardware. Last one I wanted to note here is a example of some thermal control paint. This was a sample that was taken from Surveyor 3. Whenever we did our Apollo 12 landing, we landed about 155 meters away from this previously landed spacecraft, Surveyor 3. So it's the only example that we really have of one spacecraft landing near another structure that we had previously sent and trying to evaluate how bad the damage is due to that injecta. Now the catch is that Surveyor 3 was actually down inside of a crater. So the vast majority of all this ejecta flew straight over the crater, over its head. But you know, any interparticle collisions that were occurring in that main stream of particles caused some of the ejecta to go off the main course and go down into the crater and impact the Surveyor 3. And based on this, you know, indirect kind of damage that was occurring, and there were estimates that were made that nearly 1 million times worse is how bad the damage would have been if it were actually not inside of a crater and it had been exposed directly. Uh, Even so, we still see that there's severe cracking and pitting that occurred as a result of these impacts, and detailed analysis you know, was performed on that, and those conclusions were reached. And so this you know, clearly illustrates that you know, things that you might not be obvious to you at first as a problem are they need to be thought of down to just the thermal control of your space structures. And if you are going to have something on the moon that is exposed and it requires this particular thermal uh, paint in order to keep itself cool, you're not going to be able to rely on that very long for these launch and landing events. So this last slide, I wanted to show a little video, and whenever this video gets towards the end and you start to see the lander from this Firefly lander reaching the surface, watch carefully and watch how many large rocks are flowing all the way over the horizon. You know, they're taking off at pretty high rates of speed, and you can look at the chart on the top, and this analysis has been done to show how fast the particles are leaving an area as a function of particle diameter and a function of the lander you know, size class. And the you know, if you uh, do that analysis, you can see that some of the particles are um, in the range of in like sub-millimeter particles are 1 millimeter, you know, and below are in the range of like as fast as a bullet or coming from a gun. Whereas the finest particles down 10 microns or 20 microns or so and below actually starts to get to the escape velocity of the moon. So this is puts into perspective just how fast these particles are going and just how much energy is in these particles whenever they're accelerated by the plume. So it is it's sandblasting and it's you know, throwing chunks of rock, and it's has the tendency to cause lots of damage. And you're not safe if you go just a kilometer away or something like that and assume that oh, you know, it's going to be fine. This is a an effect that is going to be felt by the entire lunar surface. Whenever you land, particles will be propelled all the way around the moon, and some of them will be sent into lunar orbit. So this could not only affect the structures on the moon, but also could affect things like satellites going around the moon, Gateway or other communication satellites around the moon that need to be planned for in their logistics around all the landing events. And you know, then the question is, how long are the particles going to stay in orbit and continue affecting things? So this the impacts are far-reaching. They're severe, and we can't you know, assume that it's going to be fine and wait until these problems actually start impacting all of the space infrastructure that we're putting on the moon, because by that time it's going to be too late. And What we're showing here, we're actually working on a publication with Dr. Phil Metzger, who's just the director of the Stephen Hawking Center for Microgravity Research and Education at UCF. He's a retired NASA physicist and founder of Kennedy Space Center SwampWorks. And so we're working on him on a with him on a publication that's going to show exactly how much it costs not to build a landing pad. And I think that's important to do because the cost of building a landing pad is significant, and because it's not cheap, uh, there's a tendency to try to explain away why we may not need it, and so this tendency is in psychiatry kind of referred to as motivated reasoning, where you want to try to explain what you wish were true. Um, but we by directly addressing the cost and explaining what the cost impacts are going to be of not having it, we think this is going to be a good way to dispel any of those notions. So there are many, many, many quantifiable risks of not having a landing pad, and that publication will be out very soon. So keep an eye out for that. The take-home point, though, is that it is cheaper to build a landing pad than not to build a landing pad. And if we do not build a landing pad, our assessment indicates that it's quickly going to become economically unfeasible for long-term, establishment of human presence on the moon or Mars. All right, so let's talk about Mason's technological development. Where are we at? Because we want to solve this problem. We've identified that it is a problem, and we really want to help facilitate, humanity's expansion into space and a long-term presence on the moon and Mars. We want to support those commercial and scientific endeavors, and this is our attempts to help give the infrastructure that is needed here. So, as I said earlier, Mason is a tipping point that started in the middle of 2023, and we had humble beginnings of getting our feet wet and using some of the easily available kitchen appliance like microwaves that you would find just at your local hardware store or whatever to try to learn some things, important things about how these different simulants are respond to microwave energy. But we very, very quickly accelerated our efforts and got into relevant environment testing, and the first dipped our toes into that space at the end of 2023 with some very rough, vacuum kind of testing as a way to initially dip our toes in. But then over the next 6 months, we had just amazing, leaps and bounds of improvements very quickly with the team, and I'm very proud of them and all of the hard work they put in, the advancements they made in terms of getting an ultra high vacuum testing, getting good quality, high density, high strength of these centered materials, and also really working on the grading and compacting processes as well, demonstrating these tools in advancing those very important site preparation capabilities. The so much effort, in such a short amount of time, especially in 2024. So many advancements as we then went into our TRL5 testing, started making larger and larger, samples and scaling up things. And the next several months is going to be very exciting. We've been recently preparing for our upcoming TRL6 testing. We passed our CDR, and the team is getting hardware built right now to support that upcoming testing. That'll be occurring at Kennedy Space Center's Swamp Works facility. All three of the tools will be tested over there. And so yeah, we're rapidly coming towards that time. Very exciting time for the culmination of all this effort. So let's talk. I want to give just a brief snapshot of some of the testing results we've done so far. I unfortunately can't share like everything. I wish I could, but this talk has to have a defined time limit, and I would be here all day talking about all the different testing that we did. But there's quite a bit. And all the great things that we learned in all three of these processes. But we'll just give a high-level snapshot of some of the most important kind of takeaways that we've done from testing so far. That, in my opinion, given the time constraints here. So first off, we'll talk about the base testing, doing our grader testing. And I'll play a couple of videos here that show you how that testing was performed. I really like videos and images to kind of show off exactly what we were doing during the testing. And if you look at the video on the top, we were demonstrating rock removal to be able to eliminate rocks from the area that you don't want as you're doing that initial site preparation. And in the video in the bottom, we're characterizing the forces that are required in order to push along a surcharge with that greater blade. And in our testing, we explored a matrix of three different cut depths and three different regolith densities to be able to get a wide range of conditions understood. And we developed some predictive models based on some approaches presented in literature with that are going to be that were compared against our empirical test results. And the model, it actually revealed what we learned, our takeaway, an important takeaway is that there's very high sensitivity in the model to density and cut depth. So if you are going to be trying to do this sort of testing, it's very, very important your surface prep prior to executing a test, having exceptional knowledge of the cut depth, very precise is going to be very important, and very good knowledge of the density is going to be very important. And those were very, pretty challenging. Just the site prep in between runs and having a really good understanding of, what was occurring for each particular run in those very important conditions. So. But the team learned a lot of great lessons learned about site prep and how to do it well, and how to characterize the surface along the way. And the take home here is the model that we were able to develop. It agrees with the experimental trends within the precision of the test setup that we were able to execute on. And let's take a look at the next slide. This is a snapshot of all the data with the different cut depths and the different densities that we were evaluating. As expected, higher densities and higher cut depths have higher loads, and the loads increase particularly fast for the higher cut depths with higher densities. So this is, some of the uncertainties in depth of cut and some of the uncertainties in density of the regolith leads to one of the very important advancements that we're going to be making for the upcoming testing, and that is to have a force feedback, an automated force feedback in the tool that will allow it to withdraw whenever it gets too close to an overloading condition. That will prevent us from having any rover that we are mounted on lose traction from it being overloaded. So we will understand what those safe limits are for load that the rover can accommodate with its particular size and wheel designs, Grouser design, whatever it has per Becker theory, and we'll be able to ensure that we don't get too close to the limit by having this automated force feedback and withdrawal of the tool. So next up, we have the packed testing. Here's our compaction tool, and we have two different methods that were evaluated during our testing. And the first one is a spot compaction method that is shown here on the top. It is in this method, we have a constant pressure that is exerted under on the tool, and that constant force that's providing that constant pressure to the area causes a settlement. And as you're applying this force, you apply a vibratory motion to this vibratory motor that is inside of the tool, and that vibratory motion allows it to fluidize that regolith a little bit to disturb it and facilitates the settling and the compaction of that granular media underneath the tool as you are imparting that force. Now, contrast that with the raster compaction method, where we're actually not exerting a constant force down, but rather we recess the tool a fixed distance, and then we are pushing the tool forward while vibrating that vibratory motor, but maintaining that fixed recess distance. So that's the pass depth, it stays the same, and we move the tool forward in a raster pattern over the compaction area as seen in this bird's eye view on the bottom right. So two different methods, and at the end of the day, it's likely that we are going to be using a combination of both because there's benefits to each. The raster compaction method is very nice for leaving a area very smooth in its wake, whereas the spot compaction can be better for having a more effective, higher density densification of that media. So here's a couple of snapshots of the results. When we were looking at this, we did different frequencies that were tested with that vibratory motor and different pressures that we were exerting onto the surface, as well as different cut depths for the raster case. And also different contact times. I'll talk about the contact times on the next slide. But looking at in this chart, I like this chart because it makes it pretty clear that the 71 hertz, which is the highest of the frequencies that we attempted, it pretty much works no matter what you do. We had a minimum success criteria of having 80% relative density, which is represented by the dotted line on this chart for our particular simulant that we wanted to exceed. So everything above the dotted line is good. And with a 45 hertz, 7 kilopascal, kind of a trials. Sometimes it works, sometimes it doesn't. Sometimes things are below the line, sometimes they're above. With 0 hertz at 7 kilopascals, no, it does not work. But if you just increase the frequency to 71 hertz with 7 kilopascals, every time it's going to work, with a wide, very wide margin. Now we have also tested higher compaction pressures as well, an order of magnitude higher with 70 kilopascals. And interestingly, we don't really see that much difference between a 71 hertz 7 kilopascal test and 71 hertz 70 kilopascal test. So the addition of that vibratory frequency is really helping to amplify the effectiveness of this pressure that you're exerting onto the surface. And furthermore, we see that if you have no frequency applied, and even if you are applying a very high pressure, 70 kilopascals of pressure, but with no vibratory frequency, you actually perform worse than if you use that 71 hertz and a lower compaction pressure. So all of this data combined tells us that the 71 hertz is a really good frequency for compaction in the test that we accomplished, and that it is able to reduce the force that you have to impart onto the surface to achieve a given desired compaction density quite substantially. The raster tests, 71 hertz also did quite well. And this one, we did have one of the 45 hertz tests that performed well as well. We did not have any time for replicates to ensure that this result was reproducible, though. So we just have to take that with a little bit of grain of salt. And real quick, let's talk about the contact time. Now we have interesting note that for 71 hertz, we tried times down to as low as 8 seconds all the way up to 180 seconds, and didn't really see a difference in, like, if you are contacting the surface and doing that compaction for a longer period of time, do you get better results? It essentially suggests that we are using more time than is needed already. We've reached a steady state. So the whole process is pretty quick. In only 10 seconds, we are pretty much already maxed out at our peak. The other note is there may be a little bit of a trend here with the 45 hertz that needs longer periods of time to be more effective. But with the 71 hertz, we definitely don't see that. Now, let's talk a little bit about microwave centering. Real quick, so benefits of microwave centering, I wanted to highlight to differentiate it from some of the other alternatives that you could use to accomplish this. One of the great benefits with microwave centering for a process like centering of regolith to make landing pads or something is it's a volumetric heating method. And this is very effective in thermally insulated materials, much more effective than if you are heating from the outside in, and you're depending on that heat transfer through the powdered media, in which it doesn't do very well. So as a result, you're able to center much thicker items in one go, and then if you were just heating from the top down. Process can be scaled very easily to balance a trade between productivity and power consumption as well. And it's a very dust tolerant method just inherently. This kind of contrasts it with some other methods that might rely on things like sensitive optics, and those optics might be obscured or with some dust accumulation over time. Self-heating may start damaging them, and that sort of thing. So it's great that it's just innately pretty compatible with the very dusty environment of the lunar regolith there. The challenges, though, of working with microwave centering are significant, so we have to consider them. And propensity to develop hotspots is an issue, and that volumetric heating, it's a blessing and a curse, because whenever you heat from the inside out, it actually makes it difficult to see what is the peak temperature inside of your item, and makes it difficult for control. If your only way of achieving a control with some non-contact temperature measurement is by looking from the outside in, you never really have a good idea or of what the peak temperature is, and that makes it more difficult to prevent overheating, thermal runaway, that sort of thing. And it's just a complex phenomenon that has a lot of different properties that are difficult to measure and control. And as a result, doing accurate simulations and predictions and models off the process, can be a challenge. Um, however, as I was saying before, very proud of the team for what they've been able to accomplish in such a short amount of time with the microwave sintering process, and going from in December 2023 samples that looked like Swiss cheese. They were overheated and not very good control over the process there. Had samples with very large voids inside of them, to only a few short months away, getting to a point where we had very high dense items, very low porosity, and they were very strong. The bottom section here, subsequently during our TRL6 test, our TRL5 testing, continued advancing on that. I've got a snapshot of some of the best performance metrics to date of various different items, and these are just a snapshot in the progress over time. We're still advancing these, and I still think that there's quite a lot of room to improve upon these in the next few months, especially as we get into the larger scale testing in the assist chamber at KSC in Q4 this year. But we were able to successfully show the good control of the process, and we were able to develop some sophisticated models that agreed with our empirical our data that we were performing in the lab there. And it's very important to be able to tell if it's reproducible or not, if that process can be reproduced. So we did make sure to show that our controls are not just a fluke, one off. We accidentally got a good sample or whatever. We're able to show that with our control process, that these 3 runs are reproducing the same set of conditions over and over again, and we're getting very similar results in terms of all these metrics for the items that we're producing here. Reproducibility is confirmed, and that's great. So in the last couple of minutes here, I just want to give a picture of kind of where we're going, and we're preparing for the TRL6 testing, and I like this progression of hardware, how far we've come over the last couple of years, and the testing coming up in the KSC facilities at the end of this year is going to be very exciting indeed, and we're rapidly getting ready for that at this moment. This image, I love this image as well. It gives you an idea of the vision for how we are going to help facilitate the development of these habitats and these base of operations on the moon and on Mars. And one of the interesting things about the microwave sintering process, for example, is with the higher iron content of the Martian regolith, there's actually a higher microwave susceptibility that the Martian regolith has. So whenever we are demonstrating the tool works on the moon, it's actually going to work even better, essentially have less power requirements to accomplish the same sort of things when we go to Mars. So it's certainly transferable, and the grading and compacting tools as well, of course, and they will be very important for those as well, for those missions. And to summarize real quick, Redwire, we're committed to helping to execute that Moon to Mars initiative that NASA has, and we are developing the technology that's going to help to establish that long-term presence, and we want to be solving that problem of making the preventing the economics from being unsustainable by having the landing pads present whenever we have establish a base of operations. So all three tools, we have already successfully tested them in relevant environment, and we're preparing for higher fidelity testing to be performed in KSC in the coming months. And the last chart I wanted to show is let's see, next. Why is it not going next? There we go. Last chart I wanted to show, I didn't have a good space to put this in, but I wanted to brag a little bit about the team here. This is a radiation absorbing material that's
Hey,
compatible.
Patrick, we just see
Yes,
the question slide. I think you need to go back one. I think it might have updated on our side.
that's okay. The question slide is actually this slide.
Oh, okay.
Um,
Sorry.
so this background that you have on this slide, I didn't have a good place to fit it in anywhere else. So I just wanted to put it up and talk a little bit before we jumped into questions. That this is a custom radiation absorbing material that the team developed, and it's actually not easy to just buy a radiation absorbing material that is compatible with high power and compatible with vacuum environment and can tolerate higher temperatures and that sort of thing. So we actually had to make our own. We wanted to buy something, we just couldn't find anything essentially, and the team was able to come up with the designs and prototype them and fabricate them and the performance of these is fantastic. It's got 99.9% efficiency in absorbing the radiation, the microwave radiation that's coming towards it. And we line the inside of our test beds that we're going to be using for the TRL-6 testing are lined with this material. The importance why we do that is it makes our testing more relevant uh, to how things are going to actually operate on the lunar surface. Because in a lunar environment, it's essentially like you have an infinite depth instead of that energy reflecting back up at you. The energy is all absorbed. Anything that makes it through the regolith that you're actually trying to heat and center, it gets absorbed and it doesn't get pushed back. So our testing is going to be um, not only relevant in terms of the vacuum conditions, but that's a very important thing that I'm proud the team was able to accomplish is to make it very relevant in terms of its free field environment for the microwaves and simulating how they're going to be responding on the moon itself. With that, I just want to say thank everybody for their attention and open it up for some questions.
Awesome. Thank you, Patrick. Great talk. Yeah, we'll jump right into the Q&A. The first one we got from Gerald Jerry Sanders. Was your test on chart 25 performed in vacuum or in the lab? Please note that any vibration testing performed under atmospheric pressure will change once you go into vacuum.
So the pack testing, good question there. So, and here we did actually some testing in vacuum and some testing outside of vacuum. And we compared the two. So there's a much more detailed report, I think, that Evan and the team there at SwampWorks are publishing on NTRS. If they haven't already published it, it should be published very soon. But In that it says that it shows the figure that kind of compares what the behavior was for the vacuum testing to the ambient testing. But to answer your question directly, the results that are shown on this particular slide right here is done in ambient.
Awesome. Thank you. And thanks for the question, Jerry.
Yes, thank you,
David
Jerry.
Bemis. David Bemis asks, how do you plan to initiate the melt in cold regolith? Is there anything special besides the standard microwave?
So to initiate the melt starting from a cold condition,
Mm-hmm.
right? The initial heat up is a little bit inefficient, if you will. As you are, and whenever the regolith is colder, it's less susceptible to microwave energy. But once you get up to temperature and you're continuing to raster along, you're preheating everything around you already anyway, so your efficiency starts to go up, dramatically over time there. But so we have demonstrated that the in some of our early tests, kind of rough proof of concepts that uh, items that were cooled in a minus 150 freezer, could be centered in and heated up in a microwave and kind of prove that is it's not impossible to get it over that hump. And in the testing that we have coming up in the Q4 here, we're actually going to be pre-chilling the entire bed with LN2 heat exchangers to demonstrate that directly. That the starting temperature of the regolith is going to be relevant for lunar environment, and we'll show exactly how much energy it takes to get over that hump for your initial heat up.
Awesome. Thank you. We have a lot of questions in the Q&A, and we can go a little over 3 o'clock, but I do have another obligation right after this. So Gabriel Houston asks, is the radiation absorbing material made with sintering of regolith materials?
So the radiation absorbing material is a silicon carbide based material. So not the same as the regolith.
Wonderful. Next, Jordan Woods asks, porosity control was a direct correlation with temperature control. Was porosity control a direct correlation with temperature control during the microwave sintering?
The preventing things from overheating, does help with the porosity quite a bit. Yes. So that's the major factor is just better process control.
Awesome. Holly Schulman asks, you're not specifically saying that the largest sample and the reproduced test are in vacuum. Are they,
Uh,
and what
they were.
vacuum level? They were. Okay.
Yes.
Vacuum level?
The kilogram scale samples were at high vacuum. So in our process, we have initiate the test in like 10 to the minus 6 or so is when we start. There is some outgassing that occurs during the test due to the material itself off-gassing. So the pressure climbs a little bit during the test. But we stay in the below the like no higher than 10 to the minus 3. That's our cutoff. If we ever reach 10 to the minus 3, we say we're definitely not relevant anymore. But usually we're in the like 10 to the minus 6 to 10 to the minus 4 range over the course of the test, with the initial heat up being the where it climbs the most, and then the pressure starts to come down again from there.
Cool. Um, James Green asks, what is the mass of the landed system for one, Moon, and two, Mars?
Mass of the landing system. Sorry, what was the question again?
What is the mass of the landed system for Moon and Mars? So
Oh,
your
okay. Yeah.
systems, what is their mass?
Right. So right now we are optimizing for a smaller scale demonstration mission rather than doing the full-scale commercial system. So it's difficult for me to give you a swap for the commercial item at this time, but for a couple of brief metrics, I can say for um, the small scale demo system that we're working on. The power requirements are actually pretty low. We can do the microwave sintering for in the range of 200 to 300 watts at a smaller scale. Now that is not something that is scalable to be able to make a landing pad in a short amount of time, but it's certainly able to make some coupons for testing and characterizing, understanding how the actual lunar regolith is going to respond. And the mass of the rest of the system, I think we were targeting a somewhere in the I don't want to I don't want to say a number and it'd be wrong. Let me just follow up with if you could ask me that question, and I'll check with our engineers, and I'll actually give you the right answer for the small scale demo that we're doing.
Awesome. Is it okay if I punch your email
Yes,
into the chat here?
absolutely.
Okay. Sorry, hold on. And while I'm doing that, I guess should ask the next question. Let me bounce back here. David Carrier asks a question that, yeah, seems like David Carrier would ask this one. Also on chart 25, if
Yep.
1.7 grams per cc is 80% relative density, what was the density at 0 and 100%? So what are your minimum and maximum densities of the simulant?
Right. Off the top of my head,
Did you, what simulants was it? Was it Exolith simulants?
this one was BP1.
Okay, I didn't.
And I think it was around 1.9 was the 100% relative density, but don't quote me on that. The minimum I can't remember.
No problem. I am still struggling. All right, everybody, I am punching Patrick's email address in the chat, so you should be able to see that. Last question we'll take for today is from Holly Schulman again. What is the frequency range for the variable frequency?
Good question. So 5.85 to 6.85, I believe, or 5.75 to 6.75, actually, I believe it is the gigahertz range that we're working with right now.
Awesome. I think that is the last question in the Q&A. Also, in the chat, I just put a link to the AIAA Space Resources Technical Committee's YouTube channel, where we will actually be uploading this recording for you all to view after this. That said, we are a little over time. Patrick, lots of great questions, lots of great engagement. Thank you for sharing all the work that you and the Redwire team have been doing. Everybody, stay tuned for next month's announcement. Thank you for attending. Um, and I hope to see you next month. For now, I'm Jared Longfox. I look forward to seeing you all again. And thanks again, Patrick. Great talk.
Thank you.
Bye, everyone.